Okay, this is going to be a little bit longer lecture, so again, strap in, hold on tight, and let's get through telescopes here, okay? All this slide is trying to show you is, and I don't like talking much about it, is that the light coming from astronomical objects, whether it's a distant star, a distant galaxy, a planet, our sun, the moon, the light coming from these objects is coming into the earth straight in, not at some angle. We can't see light at an angle. We can only see light that's coming directly into our eyes. So the only way we can see these objects from space is because the light coming from them, once they get here, is coming straight into the earth. And that's what this slide is trying to show you. And this is what lets telescopes work, is the fact that the light is not coming at an angle, it's coming straight into the telescope. Okay? Okay, there are different kinds of telescopes. The two that we're going to primarily concentrate on in this class are what we call optical telescopes. We call them optical because they are used with our eyeballs. There are telescopes that are used to see the entire electromagnetic spectrum. Optical are used to look at the visible region of the electromagnetic spectrum. Okay. There are two types of optical telescopes. You have the refracting telescope, right here, refracting telescopes, and you have reflecting telescopes. Now, remember what I said about Newton. Newton is the one that kind of invented this reflecting, the Newtonian telescope. It's the kind we have here at school. It's the kind that's only used for research today. Newtonian telescopes are reflecting telescopes. The kind Galileo used are refracting telescopes. Those are hardly used anymore, I don't think at all, for research, because the quality of viewing you get through a refracting telescope is not as good as a reflecting. Now, what are the differences? Let's talk about refracting telescope first. A refracting telescope uses lenses, just like your eyeglasses, okay? It has a lens at the front of the telescope, and it has a lens back here at the eyepiece of the telescope. Light comes in. Remember, a lens is just like a prism. It causes the light to bend down towards the eyepiece lens, okay? So you got light coming in through the front lens. It causes the light to reflect down and passes through the eyepiece lens so that you can see it. Now, magnification of a telescope is not done by the front lens. This front lens is called the primary lens or the objective lens. One of those two names, write both of these down. The primary lens or the objective lens is the big lens that's on the front of the telescope. The eyepiece lens is this little tiny thing, okay? But all magnification from a telescope comes from the eyepiece lens. Telescopes do not magnify objects. Magnification produced by a telescope is bad. The more you magnify the image, the worse it's going to look. Okay, so let's just get that done and over with. Primary or objective lens up front, that's the big lens, eyepiece lens at the end. So refracting telescope is a long tube, primary, eyepiece lens, magnification comes through eyepiece lens. Remember, magnification is bad. Here in a second, I'm going to tell you how telescopes make images look big and pretty here in just a second, okay? The second type, the kind we use now today for the most part, reflecting telescopes. Again, normally they're a tube shape, okay? Let me go get one so you can see it. Here's one of the ones that we have here at school. This is a reflecting telescope, whereas a refracting telescope used a lens in the front and an eyepiece lens in the back. Reflecting telescopes, reflecting, so you're talking about a mirror type of thing going on, and that's exactly what they use. Reflecting telescopes, there is nothing, if I can get this off of here, there is nothing in the front. The mirror is in the back of the reflecting telescope, and the eyepiece is back here too. So what you have happening is the light comes in, it hits the mirror in the back, okay, so it hits the mirror here in the back. It will reflect up a little bit and hit another mirror right here, and this secondary mirror, primary mirror, objective mirror in the back, secondary mirror here, So the light comes in, hits the primary, secondary, bounces to the, hits the primary, bounces to the secondary, and then the secondary takes the light and sends it into the eyepiece lens here, okay? So with a reflecting telescope, you have a mirror and a lens. Mirror and a lens. Refractor, you have two lenses, okay? Now, when you look at these, when we do come back to school, you'll notice that yes, there's a piece of glass here. This is not a lens. This is a piece of glass, and what it does is it keeps dirt and debris from getting down in the tube because you don't want to scratch or break the mirror, okay? So, reflectors use mirrors and lenses, and refractors use two lenses. And don't forget, the kind that we use today is reflectors if we're talking optical telescopes. Okay, so if magnification in a telescope is bad, how does it make objects look so big and clear? It has something to do with what we call light gathering power, okay? The bigger the objective lens or mirror is, the more light gathering power it has. The more light gathering power that it has, the bigger, clearer, and more resolution you will have in your telescope. So in this example here I have my objective or my primary mirror. Here's a different telescope with a primary objective mirror. You can see that the objective primary mirror on the right-hand side is bigger than the one here on the left-hand side. When you look at the image that this telescope is looking at with these sizes of primary mirrors, the one on the right is bigger, clearer, and has more resolution to it. So the bigger your objective lens or the bigger your objective mirror is, the bigger, clearer, and more resolution your image will have. It's not magnified. It's based on light gathering power. Now you take an eyepiece lens and you get a really high magnification light eyepiece lens and you put it on this telescope, you're going to screw this image up. No. Whenever I'm using an optical telescope, I never use, try not to ever use an eyepiece lens that's over 2.5 times magnification, okay? There's no need for it. If you want a nice, big, clear, high-resolution image through your telescope, then you've got to spend the money and get a good one that's got a larger objective lens or mirror. The bigger that is, the better your image is going to be. So this is how telescopes do their thing, light gathering power. All right? Okay, skip those next couple of slides. I've already talked about those. Eyepiece and refracting, I already talked about that. Skip this lens, okay? This is an example of what a refracting telescope looks like. It's a great big long tube. Up here, you have the objective or primary lens. Down here, you've got the eyepiece, okay? This happens to be a giant refracting telescope at Yerkes Observatory. Right now, I believe this is the largest refracting telescope that we have, okay? When I was learning how to do astronomy and learning how to be an observational astronomer, I used the sister to this one here. It wasn't as big as this one, but it was built, designed exactly the same way, and it was built, designed after the Yerkes Observatory here. Okay, to get an idea of how big this telescope is, in your PowerPoints that you're looking at, this right here, that image right there where you see that flash of light, that's a human being. That's how tall the human is. It's an adult human being. This is a rather large refracting telescope. This is one of the problems as to why we don't use them anymore, because you can only build refracting telescopes so big. It comes a point if you build them too big, they will break on you, and other things will happen. But yeah, we don't use these anymore because the bigger you make them, the quicker they'll break. All right? There are one of the problems other than the bigger you make it, the quicker it'll break on you. The bigger you make them, the quicker the primary lens will sag on you due to gravitation pulling on the lens because it's heavy. It undergoes something called chromatic aberration. Remember, it's a lens. The lens acts like a prism. So when the starlight passes through, or the light from the moon or the light from a planet passes through the lens takes that light and splits it up, refracts it in different, because of the different wavelengths of light in white light. And so what will end up happening is the blue light and the red light and all the other lights, colors of light going from red to blue, will focus at a different point, so you can't get a good sharp image, okay? It's called chromatic aberration, and it caused a lot of problems, and it was difficult to get really true, good, clear images, okay? So there was a fix for that, and what we did was we would put a pair of glasses, which is what this lens right here is, a pair of glasses on the lens itself. Just like when you wear glasses, it forces the light entering your eye to focus at one point. The reason you have to wear glasses is because your eyes won't focus all the light at one point. Glasses do that. So we put glasses on these things, caused all the different colors of light to focus to the same point. Fixed the problem. The problem is, guys, just like your eyeglasses are expensive, these were extremely expensive, so it was becoming extremely expensive to fix all of the research-grade refracting telescopes that we had in the United States back in those days to deal with this. Plus, again, you still have the fact that the bigger you make that lens, the quicker it sags, the quicker it'll break, okay? So Newton developed years ago the Newtonian telescope, the reflecting kind. What you have is you have light coming in, it hits the mirror. Now for years and years and years, and this is how Newton built them back when he did it himself, the mirror was what we call a spherical shaped mirror, like you see here, spherical shaped mirror. It's just a shape of the mirror. Spherical shaped mirrors will not reflect the light to the same point. Depending on where the light hits the mirror will depend on where it focuses. So remember, I told you that in a reflecting telescope, light comes in, hits the mirror, reflects to a secondary mirror that then reflects it into the eyepiece. Well, if I can't get all the light to hit the secondary mirror properly, I'm not going to get a good clear image. It's going to be fuzzy. So the fix for that for the longest time was again to put a pair of glasses onto it, forcing the light when it comes in to all focus at one point. So then you'd put your secondary mirror there. That was expensive, guys, just like it was for the refracting kind. Then some brilliant physicist, and keep in mind astronomers are physicists too, I don't know why this wasn't noticed much earlier than it was, said, hey, stop making the mirror spherical. Make the shape of the mirror parabolic. And by making the shape of the mirror parabolic, it doesn't matter where the light hits a parabolic lens, it all focuses at one point and you don't have to put a pair of eyeglasses on it. So now, all research grade telescopes, to include the ones we have here, excuse me, on campus, have parabolic mirrors. I don't think they make reflecting telescopes with spherical mirrors anymore. I think they're all made with parabolic mirrors. Okay, so they all will automatically focus the light all at one point. All right, so it fixes that problem. Okay, also having a mirror versus a lens, you don't have to worry about gravity causing the mirror to sag, and therefore you don't have to worry about gravity causing the mirror to break. Because remember, it's down at the base of the telescope. It's being supported by the base of the telescope. That lens in the tube of a refractor, it's only being supported by the edge. There's no support in the middle, so gravity causes it to sag and eventually it'll break. A huge waste of money, trust me. Okay? Okay, we've talked about optical telescopes. Those are the kinds that we used to look through with our eyes. There are other kinds. We have radio telescopes, we have microwave telescopes, we have infrared telescopes, we have ultraviolet telescopes, we have X-ray telescopes, and we have gamma ray telescopes. Again, astronomers want to look at all these different wavelengths of light because there are objects in space that produce all of these wavelengths of light. And so we want to study these objects, so we have to have telescopes that can do that. Okay? What you're seeing here are radio telescopes. These are in Socorro, New Mexico. This is called the Very Large Array. Okay? These telescopes, each one is very, very large. The shape of the dish, we call this a dish. The shape of the dish of the radio telescope is the same shape as the mirror in a reflecting telescope, parabolic. Therefore, when the radio waves hit the telescope, doesn't matter where they hit the dish, they will all focus at that point right there in the front, okay? Now, why is there so many of them here? Why not just one? Because what we found was that we can, through a computer, electrically tie these radio telescopes together to emulate a much larger radio telescope. Remember what I said about light gathering power. Let's just talk about reflectors because that's what we use today. The larger the mirror, the more light gathering power, the bigger, better, clearer your image will be. I don't care what frequency of light you're looking at, it's the same thing. So we want to make these dishes as big as we can because the bigger they are, the better light gathering power they have. Problem is these are made of steel. You make them too big, they're going to collapse under their own weight. So what can we do about that? Well, I can put a bunch of them together, tie them together electrically via a computer, and emulate a much larger radio telescope. So you can see how big each of these are. Now, if I put them in this configuration like you see here, and I tie them together through a computer electrically, and I have them all pointed at the same object, like a black hole, we use these to study black holes with, I can emulate a radio telescope that is that big, okay? This is much bigger than each of these individually. This would give me excellent light gathering power. Now the thing about the VLA, if you're looking at your PowerPoints, which you should be, there's a railroad track next to each of these. It goes out 5 miles in each direction. So I can take these, put them on the railroad tracks and spread them out over a 5-mile distance on each of these legs. That would mean now, once I tie them together electrically and have them pointed to the same object, I would be making a radio telescope that was gigantic, okay? So you can tie these together and make a larger telescope out of a bunch of them. It would act like it's one single telescope that would have a monstrous light gathering power ability to it. Therefore, the clearer, better resolution your images are. Especially when we're talking about black holes, we want the best resolution we can get. We want to see all the detail that's possible with a black hole, okay? Come to find out, you can do these with optical telescopes as well. Won't get into that, but you can tie any type of telescope together, a bunch of them together to make a much bigger one with much larger light gathering power. This is just a picture of the Hubble Space Telescope. The Hubble Space Telescope is an optical telescope. Why did we make an optical telescope so we can put in space? Because the atmosphere messes with the image. When light comes through the atmosphere is not static, it's dynamic, it's moving around, okay? So if this represents the Earth, and here's my observatory, okay, right there. Here's the atmosphere around the Earth, like so, okay? And I'm looking at a star that's over here. There's my star, okay? The light coming from that star will go straight as an arrow as long as it's in space. So here comes the light from that star, straight as an arrow. It hits the atmosphere. Once it hits the atmosphere, it starts to jiggle, okay? And the deeper that light gets into the atmosphere, the more the jiggle is. Now, I'm going to over-exaggerate this. It's to make a point, okay? So here comes the light in space, straight as an arrow. It gets to the Earth's atmosphere. It instantly starts to jiggle. And like I said, the deeper in space it gets, the jiggle gets worse. And by the time you get the light to the telescope, you're looking at an image that's doing this. You can't get a good, clear image like this, okay? So, build the Hubble Space Telescope, put it in space. There it is, right there. Light comes right straight into it. No jiggling, no nothing. Now, This is expensive. A method we use now today is much less expensive, and we don't need to put optical telescopes in space. Give me just a second. There's a method we use to do away with having to put those telescopes in space. Let me put this on pause. I'll be right back. I've got to run and do something real quick.